So, we discussed about eigenvalues and eigenvectors. We also discussed about the properties of eigenvalues and eigenvectors and some of the interesting relations arising with eigenvalues and eigenvectors. And as promised, this class I will devote on looking into eigenvalues and eigenvectors of real symmetric matrices, because they pose certain interesting characteristics here. And also at the end we will try to look into the solution of rate equations using eigenvalues and eigenvectors, which will be important in the context of iterative methods, which will follow later. So, if we move away, eigenvalues and eigenvectors are in general complex numbers. Why? Because eigenvalue of the matrix is obtained as the root of roots of polynomials of order n. If A is we must write that A is n into n, then this is a polynomial of order n, and this is obtained as determinant of A minus lambda I is equal to 0, which will be an equation of polynomial of lambda is equal to 0. And if we write down the equation, this will be lambda to the power n minus trace of A lambda to the power n minus 1 up to minus 1 to the power n determinant of A. So, and this will also follow that if we look into this equation and equate this, that p lambda is equal to the roots of the eigenvalues are lambda, the eigenvalues are lambda 1, lambda 2, lambda n, which are roots of the polynomial lambda minus lambda 1 into lambda minus lambda 2 up to lambda minus lambda n. And we compare the coefficients of say lambda to the power 0 is equal to minus 1 whole to the power n, lambda 1, lambda 2 up to lambda n. And if we compare these coefficients, then we get determinant of A is equal to lambda 1, lambda 2 up to lambda to the power n. Similarly, if we compare the coefficients both sides, from both sides the coefficients of lambda to the power n minus 1, we will see that minus lambda 1 plus lambda 2 up to lambda n is the coefficient which is nothing but trace of A. So, trace of A is equal to lambda 1 or rather minus trace of A plus lambda 2 up to lambda n. So, these are the can quickly show the two propositions we obtained as the properties of eigenvalues in the last few lectures, that sum of the eigenvalues is the trace of the matrix, which is sum of the diagonal elements of the matrix, and product of the eigenvalue is the determinant of the matrix. So, now it is also can be seen if a matrix is singular, the determinant is 0. Right? The volume in the columns are dependent on each other, therefore, volume encompassed region, volume of the region encompassed by different vectors columns will be 0, because it is not making an nth dimensional enclosed volume. So, if the determinant is 0, then one of the lambda must be 0. So, for a matrix whose columns are dependent, which is a singular matrix, must have a 0 eigenvalue, which we already discussed that a singular matrix has a 0 eigenvalue. So, this can also be shown from this definition. Okay. Fundamental theorem of algebra tells that there will be complex roots or complex eigenvalues. If I have an equation which is nth order, which is an nth order equation of nth order polynomial of lambda is equal to 0, this must have complex roots. Complex roots, or which are complex eigenvalues. A real number can also be thought of a complex number with the 0 imaginary part, but the solutions will in general come as the complex form, or there will be complex roots. If lambda 1 is a complex eigenvalue of a real matrix A, so lambda 1 is a complex number, it has an imaginary part, let us assume Ax is equal to lambda x, and x will be the corresponding eigenvector. So, if x lambda if lambda 1 is complex, A is real. So, a real number multiplied with some vector gives a complex number into a vector, x must be a complex vector number, x must be a vector with complex number. A real number multiplied with a complex number can only give us a complex number, because this is complex. If x is real, a real into real cannot be a complex into real, a real into complex can be complex into complex. Therefore, if lambda is a complex eigenvalue, the eigenvector x is a complex number. So, we are this can come like kind of a shock here, because we are discussing everything with real number. If you can recall, we have discussed about transpose of matrix, symmetric matrices. We have not discussed about Hermitian, because we did not want to go into the complex number plane. However, everything being real, we can still have unreal or complex eigenvalues with imaginary components there, and if the eigenvalue is complex, if the eigenvalue has an imaginary component, the eigenvector will also be component. And interestingly, in this case, of course, we can say that the eigenvector will not be a basis of the column space, because if it is a complex number, because column space is spanned by real numbers. So, this will be another class of problems. However, if we see that lambda is it is possible to have a complex eigenvalue, and that case x will also be a complex number, the eigenvector will also be a complex numbered vector. So, x will not belong to Rn. So, the question is that is it possible for distinct eigenvalues? Let us see. Eigenvalue of a real matrix are complex conjugates. Eigenvalue of a matrix A is obtained as roots of polynomial of n, and if lambda 1 is complex root of polynomial with real coefficient, its complex conjugate is also a root. So, if I have lambda 1, or if I have lambda 1 is equal to A plus I b, there has to be a lambda 2 which is lambda 1 bar, or which is equal to A minus I b. In case A is a real valued matrix, all the components of A are real, then it has to be there. Eigenvalues will be complex conjugate. In case eigenvalues are complex appearing in complex conjugates, eigenvectors will also appear in complex conjugates. So, that means if A x 1 is equal to lambda 1 x 1, x is a complex number, A x 1 bar is equal to lambda 1 bar x 1 bar, and lambda 1 and lambda 1 bar are complex conjugates, and x 1 and x 1 bar are complex conjugates. So, we can have lambda 1 lambda 1 is equal to A plus I b, lambda 1 bar is equal to A minus I b. Similarly, we can have x 1 is equal to x 1 plus I y 1, x 2 plus I y 2, so on x n plus I y n. Then lambda 1 bar will have a corresponding eigenvector, which is x 1 minus I y 1, x 2 minus I y 2 to x n minus I y n, and only if we have this, only then we can have a real matrix A for which these are eigenvalues and eigenvectors. Otherwise, if it they do not appear in complex conjugates, the matrix is not a real matrix. Okay. So, what we got is that for real matrix, the eigenvalues and eigenvectors will appear in complex conjugates, if at all they have some imaginary component, and they may be complex, they may be imaginary, there may be imaginary component using the fundamental theorem of algebra, that we can say. Now, we will look into the symmetric matrix. eigenvalues of a eigenvectors of a symmetric matrix. Let lambda and mu be two distinct eigenvalues of a symmetric matrix A, and u and v are the corresponding eigenvectors. So, you can write A u is equal to lambda mu u, and A nu is equal to u and nu are the eigenvectors. So, sorry, u and v are the eigenvectors, A v is equal to lambda v. U and v are the eigenvectors as corresponding to eigenvalues lambda and mu. So, we can write u transpose A v, and A v is equal to mu into v. That is what we are getting from here. So, u transpose A v is equal to u transpose mu v, and as mu is a scalar, that will come out. So, mu u transpose v. Again, u transpose A v is equal to transpose of v transpose A transpose u by the transpose product rule, which is v transpose A u, and A u is nothing but A u is nothing but lambda u. So, substitute here is v transpose lambda u transpose. So, lambda is a real number, is a scalar. So, lambda will come out of this, and this will be v transpose u whole transpose, which is u transpose of v. So, you get u transpose A v is equal to mu u transpose v, and u transpose A v is equal to lambda u transpose v. So, if we equate them as, and this is done as A is symmetric. So, A transpose is equal to A as A is symmetric. So, if we equate them, mu u transpose v lambda u transpose v is equal to mu u transpose v, and for this is this for distinct lambda and mu, which is not possible. If lambda and mu are different and u and whatever is u and v, u transpose v has some value. If lambda and mu are different and u and v, it took that there are distinct eigenvalues. So, u and v are non-zero. This is not, they are non-trivial solutions. So, u transpose v is a non-zero number, then we cannot have sorry, we did not think u transpose v is sorry. If lambda u transpose v is equal to mu u transpose v, the only possibility is that lambda is not is equal to mu, that is told, lambda is not is equal to mu. So, the only possibility is that which I say it is non-zero is not true. U transpose v is 0, A into B is equal to C into B, A and C are different. This is only possible when B is equal to 0. So, what we obtain that for a symmetric matrix u transpose v is equal to 0. So, the eigenvectors associated with distinct eigenvalues are, or we can write eigenvectors are orthogonal. For distinct eigenvalues, the eigenvectors are orthogonal to each other, and this is for a symmetric matrix. For a real matrix, eigenvectors appear in complex conjugates, and we got from a sort of symmetric vectors matrix, eigenvectors are orthogonal to each other. So, now we have to see what happens. We earlier obtained for any general matrix, eigenvectors are linearly independent. Now, what we are seeing, eigenvectors are orthogonal to each other too. Linear independence means, orthogonal means linear independence. Linear independence does not necessarily means that they are orthogonal, but orthogonal means they are linearly independent. So, that is fine, that this still substantiates they are linearly independent. However, this orthogonality is only for symmetric matrices. For any general matrix, we cannot show that they are orthogonal to each other. Only if we can do this step, A transpose is equal to A as A is symmetric, we can say that mu u transpose v is equal to lambda u transpose v, and now as mu and lambda are distinct, u transpose v should be 0. Okay. So, we got for a what will be eigenvalues of for a real symmetric matrix. we got that eigenvalues for a real matrix are will appear in complex conjugates and eigenvectors also, and eigenvectors for a real for a symmetric matrix will be orthogonal to each other. So, what will be the case for a real symmetric matrix? Eigenvalues of a real matrix A appears in conjugate pair like lambda and lambda bar. As if A is a real symmetric matrix, then the corresponding eigenvectors are orthogonal. Lambda and lambda bar are two distinct eigenvalues. So, the corresponding eigenvectors must be orthogonal. Therefore, the eigenvectors will also appear in conjugate coordinate. If one eigenvector is x plus lambda y, the other eigenvector must be x minus lambda I y, x plus I y, the other must be x minus I y. They are complex conjugates. So, as they are complex conjugates too. So, we should get that symmetric, we assumed A to be real symmetric matrix. Symmetric matrix has orthogonal eigenvectors for distinct eigenvalues. Therefore, as they are distinct eigenvalues, x plus I transpose is in dot x plus I dot x minus I y, x plus I transpose into x minus I y is equal to 0, which gives us x transpose x plus y transpose y is equal to 0, or L2 norm of x plus L2 norm of y is equal to 0. And when it is possible? When this implies that x and y are both 0 and eigenvectors are 0 vectors. However, eigenvectors cannot be 0 vectors. That is what we are discussing for a while, because eigenvectors only appear when A minus lambda I has a null space. If for any value of lambda A minus lambda I becomes a singular matrix, only then eigenvectors appear, and eigenvectors are linearly independent, they cannot be 0 vectors. So, this is not admissible in case A is non-singular. In case there are non-zero eigenvalues of A, this is not possible. So, we cannot have, this is not admissible means we cannot have eigenvectors which are x plus I y and x minus I y. This is not admissible. Therefore, we cannot have complex conjugate pairs as the eigenvalues of A. However, if there is one complex number as eigenvalue of one real symmetric matrix, it has to have another complex number. So, the only possible is that these eigenvalues are not complex numbers. Eigenvalues must be real numbers, therefore, there is no question of having complex conjugates as the distinct eigenvector as the eigenvectors of the distinct eigenvalues of A. So, what we end up is that we cannot have conjugate pairs lambda and lambda bar as eigenvalues of real symmetric matrix, as they will give 0 eigenvectors. Therefore, real symmetric matrix can only have real eigenvalues. So, eigenvalues of a real symmetric matrix, of a symmetric matrix with everything belonging to R n, with all the real numbers as its entries, must be real numbers. This has a very important implication, especially when we look into symmetric matrix, because we are dealing with only real numbers in those cases. Then comes another interesting concept of similar matrices. The matrix A and M inverse A M, they are similar when M is an invertible matrix. If M is an invertible, M is any matrix, an invertible matrix. So, looking into M inverse A M, we can vaguely remember relate with the matrix S inverse A S, which is a diagonal matrix, and we will see if we can choose particular values of M, we will arrive into a diagonalization of A in a way. So, A and M inverse A M are similar when M is an invertible matrix. Suppose B is equal to M inverse AM, then A and B will have same eigenvalues. Right now we deviated from the symmetric matrices, this is for any general matrix. But that is M inverse x is equal to lambda x, as A is equal to, we can probably write it as A is equal to M inverse AM, as B is equal to M inverse AM, we can write that A is equal to MB M inverse. Now we have Ax is equal to lambda x. So we can substitute this here, and write MB M inverse x is equal to lambda x. And take M inverse in the right, multiply it with M inverse. So B M inverse x is equal to M inverse lambda x, which is B of M inverse x is lambda M inverse x. So M inverse x becomes lambda is an eigenvalue of B and M inverse x is the corresponding eigenvector, because it is basically B in y is equal to lambda y, and M inverse x is any variable, any vector y. So, B y is equal to lambda y. So, what we get? Eigenvector of B is M inverse x, eigenvector of B is M inverse x, which is this eigenvector, and A and B have same eigenvalues, which is lambda. So, this obtains from the definition of symmetric matrix. A and M inverse AM are symmetric and they will have same eigenvalues. The matrices A and B represent the same linear transformation with respect to two different bases are similar. If A and B represent same linear transformation, but they are with respect to two different bases, then A and B are also called similar matrix, and this property is all. However, more important example of this property is that, say there is an unitary matrix M is equal to U, and what is unitary matrix? Unitary U has orthonormal columns, and unitary matrix, and U is a rectangular matrix, and unitary matrix is a rectangular matrix with orthonormal columns. A square matrix with orthonormal columns is called an orthogonal matrix. A rectangular matrix with orthonormal column is called a unitary matrix. So, if M is equal to U, then U inverse AU, if we consider a orthonormal rectangular matrix with orthonormal columns, U inverse AU will give us a triangular matrix T. So, they are again similar matrix. So, eigenvalues of A, and as this is a tridiagonal matrix, as this is a triangular matrix, when we try to form the characteristics equation, we will see that the eigenvalues are nothing but the diagonals of the matrix T. So, if we can get choose one unitary matrix, multiply with U inverse AU gives us a triangular matrix T, the diagonals of T will be, and A and T are symmetric matrix, the diagonals of T will be the eigenvalues of T, and as they are symmetric, they will be eigenvalues of A also. And then comes a very important theorem called spectral theorem. Every real set symmetric matrix A can be diagonalized by an orthogonal matrix Q, and what is an orthogonal matrix? Is a orthogonal matrix is a square matrix with orthonormal columns. So, every real symmetric matrix A can be diagonalized by an orthogonal matrix as Q inverse AQ is equal to A, and we can get, and for an orthogonal matrix we know that Q inverse is equal to Q transpose. We have shown this earlier. So, we can get that A is equal to Q lambda q transpose, and lambda is the diagonal matrix also, and this lambda must be the eigenvalue matrix of A. So, as orthonormal means the matrix, the columns are orthogonal to each other, and by using suitable scaling, dividing it by suitable parameter, we can make the columns normal also, or columns of unit length also. So, which are the columns which are orthogonal to each other for a particular matrix A, which is the matrix whose columns are orthogonal to each other? For a real symmetric matrix, the eigenvectors are orthogonal to each other. So, Q is nothing but the matrix S for a real symmetric matrix, or the matrix where each column is an eigenvector of the matrix A. So, the spectral theorem writes that A can be decomposed as the eigenvector matrix into the lambda, which is the eigenvalue matrix, diagonal matrix with eigenvalues in the diagonal, into Q transpose, or Q inverse AQ is equal to lambda, or the eigenvalue matrix, where columns of Q contain the orthonormal eigenvectors of A, and for real symmetric matrix, true that the eigenvectors are orthogonal to each other. So, we can get an orthonormal eigenvector matrix for A. This is one very important theorem in the context of linear algebra, that a real symmetric matrix can be diagonalized using the eigenvector matrix as Q inverse AQ is equal to lambda, or A is equal to Q lambda Q transpose. Now, we go back to the difference equation and consider the rate equation u k plus 1 is equal to a u k. So, this is an integral part of the differential equation. We had the differential equation du dt is equal to a u, where we can write du dt is equal to u k plus 1 minus u k by delta t, which is a u k. So, a u k plus 1 is equal to a u k is the difference equation. The change in the increased value of u is a linear combination of A, and this will also appear in iterative methods. If we start from an initial value u 0, the solution to the differential equation will be u k is equal to a to the power k u 0, because every time we are going to a new updated value of u, we are multiplying u 0 by a, and then we will multiply the product again by a, and so on. Now, if a can be diagonalized as a is equal to s lambda s inverse, which is always possible, we will get u to the power k is equal to a to the power k s lambda s inverse, s lambda s inverse, s lambda s inverse u 0, and we have seen that a to the power k will be nothing but s lambda to the power k s inverse. So, we will get a matrix lambda to the we will get a matrix lambda to the power k, which is lambda 1, lambda 2 up to lambda n, and I asked you to check how it will be to the power k. Now, if we can form this matrix, we can find out the eigenvalues and the eigenvectors. We can find out how u 0 will be changed to e to the power k, how u 0 will be changed to u k after k successive steps of the difference equation. This is in a sense extremely important, because if whether u k is greater than u 0, we started with some value of u 0, whether if lambda to the power k, lambda is a k is a large number, k goes to infinity, k is 1000, and lambda is a matrix with norm more than 1. So, lambda to the power k will be a very large number, and u k will be actually infinitely large. Or if lambda is a number less than 1, lambda has a length or has a norm less than 1, lambda to the power k will be a smaller number, and u 0 will asymptotically approach 0. So, u k will asymptotically approach 0. So, what will be the value of u k will that blow up to an infinitely large value or it will come to a very small value, that will depend on the eigenvector matrix. Lambda is the eigenvalue matrix. Lambda 1, lambda is equal to lambda 2 to lambda n. It will depend on the eigenvalues, that what will happen to u k after k number of steps over u 0. And stability of solution u, that u, will it be stable, will it be go to a smaller value, will it be within a particular range, or it will be unstable and it will blow up to a very high value, infinitely large value. That depends on the eigenvalues of A, and this is stable if the magnitude or it will go to a smaller value, it will go down to a 0 value, or it will be in control, u k u to u at after kth step will be not infinitely large, or the solution is stable if lambda I, absolute value of lambda is less than 1, and that is for all, considering all lambdas. Or we can say the maximum value of lambda, maximum absolute value of lambda, we will consider all lambda, find out which one has maximum absolute value, that should be less than 1, then lambda is less than 1. Neutrally stable if there is some lambda which is equal to 1 and other lambdas are less than 1. So, u k will be u 0 always in that case. Unstable if at least there is one eigenvalue which has lambda I, absolute lambda I is equal to 1. So, lambda I, which is important for a matrix A, maximum value of mod lambda I is called spectral radius. If the spectral radius is less than 1, the difference equation will be stable equation. If it is greater than 1, sorry, this is greater than 1, I am sorry, this is greater than 1. If it is greater than 1, then the difference equation is unstable. If some lambda is equal to 1, but others are less than 1, then it will be neutrally stable system. And with this, we can probably I will briefly introduce you to another concept of positive definiteness of matrix, and but with this particular concept we can start looking into iterative methods, where we will update the solutions based on the previous time steps values or previously guessed values, and see that the spectral radius is an important parameter while looking into the convergence of the iterative methods. Thank you.